You might have heard of the most famous Euler equation, e to the I theta equals cosine theta plus I sine theta. Well, this is actually really important for vectors too. And vectors in general are just super important for physics because pretty much everything that we do, you kind of have to deal with translating vectors back and forth between, like, magnitude, angle, and then like component form and stuff like that. So what we're going to take a look at is, say we had a r theta that would be magnitude, and this would be the angle, and sometimes it's called magnitude direction. Well, let's just give ourselves a coordinate system here. We'll call this x here, and this is the y, and then let's say this was 5 meters and 30 degrees. All right, and it's pretty easy to graph this. All we need to do is just go like this. This is our 5 meters here, and here's 30 degrees. So far, so good. I'm pretty sure this is relatively easy. But let's say we wanted to translate this into component form, in which case we would sort of try to figure out, well, what is the x and y pieces of this, if we want to know how long each one of this is, x and y. And we can use SOHCAHTOA to be able to break this apart into components. How do we do this? Let's say this is the, if we know that this is theta over here, theta, then we know that this one is the opposite side, and this one is the adjacent side. So that way we can say that sine of theta is going to be equal to opposite over hypotenuse, and that's this one right here, hypotenuse. So far, so good. And then we could say that sine theta is going to be equal to y over 5 meters. And of course, we can rewrite this to say y is equal to 5 meters and sine of theta. That's pretty simple so far. Then we can say maybe that cosine of theta is equal to the adjacent over the hypotenuse. All right, and then cosine of theta is equal to x over 5 meters, which is just flipping these, it's basically the opposite. And then we have x equal 5 meters cosine of theta. And we've got a sine and a cosine over here. It's kind of reminding us of something. Let's just keep in mind that this whole translation is only going to work in 2D. What we're about to do here is 2D translation. But essentially we have dimension 1, which is this x, and dimension 2, which is this y. And we can write this like this. So we have 5 meters, 30 degrees. That's going to be equal to 5 meters cosine theta, which is the x. And then we can always have a little I or a j. I would correspond to x and j corresponds to y. And there's also the z if we were going to be in 3 dimensions. But z in this particular case is 0, but that would be k. And keeping in mind, and I'll write this in red also, that in 3D, heck, this is very important, because if you don't have a component and you want to translate it into the 3D, all you do is set that equal to 0. So that way, let's say you were doing, you had a x and a z, but you wanted to have, you want to know what y was. Well, y is just 0. This was kind of a confusing thing to me at some point. I was like, well, what do I know what the third component is? It's just equal to 0. But that's going to be in 3D. Now, it's kind of hard to go from 3D into the magnitude angle, so we're not going to really do that in this video. But it's pretty easy to go from magnitude angle into component form, which is this stuff over here. This is just component form. I guess we can write that in blue over here. Component form. Right, and that's just going to be what this will be. Plus 5 meters sine theta. I mean, hopefully this makes a little bit of sense, because this is the y section over here, or sorry, this is the x section here, x, and then this is the y. And just keeping in mind that we just denotate this with the I and then the J. All right. And what would be, if we needed to have the K, it would be 0. Shazam, just like that. And then here is Z. All right. And so, again, this is kind of how we can translate something that's 2D into something that's a component form vector, and then even toss in that 3D component over here. But we can't really go backwards from here so easily, unless this really is a 0. Then it's pretty easy to go from the zeros. But if this actually had some stuff, it would be a little bit more of a complicated operation. Anyway, we can even try to generalize this, right? Because we have R. Here's the general formula. We got this in red. You got this R theta. And all we really need to do is to translate this from magnitude angle into component form. We just say the magnitude of R, cosine theta, and then you can just toss in the I if you want. Then you have of course you have to put that. And then you have the component, the magnitude of R, sine theta, and as that's just J. So that doesn't that remind us a little bit of this original equation we had over here? We could totally see how this matches. Very, very similar to this. It's just that we don't have the I. Instead of I, it's a R. And the R is going to be on both sides. So all you do is you just stick the R cosine theta and then R sine theta, and now you have your vector. So this is kind of cool. But let's say we wanted to go from component form back into magnitude and angle. We're going to have to take a look at that in sort of a different example. So